Hello, my name is Mehul Kumar Naresbhai Gol, and today's my presentation topic is about energy extraction from the black hole. So, let's begin the journey. Black holes are so wild that at the conclusion of the life cycle of a big star, not even its own gravity remains with the core. As a star's core collapses, its momentum causes it to spin faster and faster until it collapses completely into a one-dimensional point of singularity and makes a highly dense object called black hole. A black hole is surrounded by a boundary known as the event horizon, which for a non-rotating black hole is centered at the Schwarzschild radius. At the event horizon, the escape velocity is equal to the speed of light, since general relativity states that nothing can travel faster than the speed of light. As a black hole rotates, it twists the space-time in the direction of the rotation at a speed that decreases with the distance from the event horizon. This process is known as the lens-tearing effect or frame dragging. Because of this dragging effect, an object within the ergosphere can't appear stationary with respect to an outside observer at a great distance unless that object were to move at faster than the speed of light. The static limit is the outer boundary of the ergosphere. The ergosphere is the region wherein the spacetime continuum has been deformed by the black hole to such an extent that you can enter it or leave if you can travel fast enough. The ergosphere is a region just outside a black hole's event horizon, the boundary of a black hole beyond which nothing, not even light, can escape. But light and matter just outside the event horizon means in the ergosphere would also be affected by the immense gravity of the black hole. Objects in this zone would spin in the same direction as the black hole at incredibly fast speed, similar to objects floating around the center of the whirlpool. Space-time bends in the direction of rotation due to black hole spin on the space-time fabric, which reduces as the distance from the event horizon rises. This is how it works. Roger Penrose proposed that a rotating black hole can store rotational energy in the circulating space-time surrounding its algorithm known as the accretion disk, like this. A particle falling into the ergosphere gather energy, causing them to revolve faster. They may be able to escape the black hole since they are still outside of the event horizon. Now, we might think that how is it possible? Because every time we heard that nothing can escape from the black hole. So, how we are going to harness the energy from the black hole? So, for more simplicity, I would like to give you the simplest example. Penrose realized that while we may have to travel at speed light to stay stable in the ergosphere, then we don't have to go that fast to enter. Assume we enter a whirlpool. Instead of simply floating along for a ride, we begin to plane towards the direction in which the water is moving. Our speed would skyrocket to a level considerably quicker and quicker than we could swim ordinarily. In this instance, we would progressively sink into the whirlpool center, just like wood in a black hole. But here point is that we don't want to lose a life. So, how can we save ourselves? Of course, majority of the people will say that if we find out any objects moving along with him, so he would probably use that object and he would hit that object toward the center of the whirlpool. Here, the opposite force would act as a thrust, so he can easily escape tangentially due to high velocity. For more simplicity, let me give you another example of a Penrose process, which is demonstrated by an interstellar movie. Without giving anything away, the crew of the spacecraft understands they don't have enough fuel to get to their destination in the film. When a distant space mission runs out of fuel, the crew makes one last effort to return home by entering the ergosphere of a black hole, dropping part of their spaceship and slingshotting away from the black hole with massive quantities of energy. A key role in the process is played by the algorithm. With an explicit demonstration, a brilliant physicist named Roger Penrose demonstrated energy extraction from a black hole in 1969. When we send a particle into the ergosphere of a spinning black hole, it splits into two fragments. One may have a negative energy, while the other has the more energy than the parent particle. This method of energy extraction is known as the Penrose process. Consider a free-falling particle that enters a spinning black hole with an energy E0. The particle disintegrates into two particles with four momenta P1 and P2 in the algorithm. Their corresponding conserved energies are E1 is equal to minus eta P1 and E2 is equal to minus eta P2 respectively. Because the daughter particle escapes to the infinite space, so this particle 1 has positive energy, while the second particle falls into the black hole, so it has a negative energy. Here, escape daughter particle's energy is much more higher than the parent particle's energy E0. This is recognized as the mechanical Penrose technique of harnessing energy from the rotating black hole. It's important to note that in the mechanical Penrose process, particles travel along a geodesic which preserve energy in terms of energy transmission to the splitting particle. The process results in any tiny drop in the black hole's angular momentum. The energy is extracted by converting the motion. In the event of an uncharged black hole, an individual single particle can gain up to 20.7% of its mass energy through this process. The law of black hole thermodynamics governs this process. If this process continues until the black hole loses its angular momentum, the black hole will cease to rotate. For example, a Schwarzschild black hole. Because of our current technical progress, we can't quickly travel to the black hole to test this out. However, in 1971, Soviet scientist Yakov Zeldovic presented an experiment. He suggested to use light waves, but researchers from the University of Glasgow used sound waves to prove their point. Revolving foam disks serve as a black hole which absorbs sound waves. They place a microphone on the other side of the revolving disk to detect the sound waves when measured from that point on the revolving surface. The twisted sound waves alter the pitch. If the disk spins fast enough, the frequencies change from the positive to negative, stealing energy from the spinning of a surface. The results were incredible as the rotational disc accelerated the pitch of the sound, hitting the microphone lower until it was completely inaudible. Then it started to climb again, this time 30% louder than the sound originating from the speaker. Piran and Saham characterized the Penrose efficiency as follows, which is followed by these equations where E in is the energy of the entering particle, ESC is the energy of the escaping particle, where ECAP is the energy of the captured particle. It's assumed to be negative because it's captured by the black hole. While we are still a long way from extracting energy from a spinning black hole, it's not impossible that some incredibly advanced extraterrestrial society or possibly our own future civilizers will accomplish it. However, there is one way to carry out the Penrose process that could make it possible. A large mirror comparative to a Dyson sphere, but much easier to build. Might be built around a black hole. Fortunately, the object would need to be just 10 cm thick to work and would not require a large amount of raw material. Once we have built a structure surrounding the black hole, we will need to open a piece of mirror and send electromagnetic waves within. When the aperture was closed, the wave would bounce around faster and faster. Some will be lost in the event horizon, but great majority will stay in the ergosphere. This causes super-radiant scattering, which happens when similar waves interact coherently and grow exponentially stronger. This means waves are doing resonance with each other. When make it extremely stronger or 2 raised to n times intense, It's not just a science fiction, it's a true. Thank you very much for listening.